So, I will continue the discussion as I discussed that we will use perturbation theory, and for that we have to identify the unperturbed term in Hamiltonian. So, H0 is basically taken as an unperturbed main term, okay, and its wave function also already is known from Schrodinger equation. So, this is psi n l m l, ms is included. This probably as I discussed that this both are valid. So, since H0 does not work on the spin variable, so it does not matter this wave function whether it is psi n l m l or psi n l m l ms. So, this is the suitable wave function for unperturbed Hamiltonian. So, I know wave function and also I know the energy, main part in energy, that is the from unperturbed Hamiltonian. Now, we have to, using the perturbation, these are the normal procedure of perturbation theory. So, without going into details, so but you know how to find out the expectation value. Okay. So, so for H1 term, if I find out the correction in the energy for this term, so we have to find out the expectation value. What is the procedure expectation value? So, that is basically del E for H1. So, this correction term energy is del E 1. Okay. So, one can find out is the psi star H1 psi. So, that is the procedure in quantum mechanics. Okay. So, this I have written in Dirac notation, you know, bracket notation, probably that I told you earlier. Okay. So, in bracket notation, this is nothing but psi star H1 psi. So, that has been written in Dirac notation, bracket notation. Okay. So, whatever H1, now put H1. H1 is basically here H1 one can write in this form is basically p square by 2m square. Okay. So, p square by 2m, from here you can see this H0 plus z d square by r. Okay. This square term square is there. Now, if you put H1 here, okay, and square, if square is there, so it will be H0 square plus 2H0 j d by r plus j d square by r whole square. Okay. So, now these three term, it will be operated on the psi, and you will get the, if it is eigen value equation, eigen equation, then eigen value you will get. So, H0 is basically if you operate on psi, so it will give En. Okay. So, H0 square, so En square, here it will give En. Now, you have to find out the average expectation value for 1 by r. Okay. Average value, expectation value of 1 by r for this psi. Okay. And similarly, other term, its expectation value of 1 by r square. Okay. 1 by r square expectation value one has to find out. So, if you find out, I am not discussing in details, but it's one has to do few steps, and one has to know, use the this different operators operation. Okay. For calculating this. So, if I avoid this calculation, but just if I write the result, so you will get this the result minus En z square alpha square. Now, this alpha is not this in Dirac Hamiltonian or whatever alpha and beta we use. So, this alpha is different. This is a basically fine structure constant. Okay. Earlier we use this alpha for fine structure constant. So, this alpha is not same as this alpha in Dirac Hamiltonian. Okay, this is alpha is basically here alpha is fine structure constant, fine structure constant. Okay, so now so what we got, del E1 equal to En z square alpha square by n square 1 n by L plus half minus 3 by 4. Okay. So, this is the correction term for H1. Okay. This is the correction due to the relativistic consideration. Okay. So, this is the for H1. Similarly, one has to find out for H2 and H3. H2 and H3. So, H2 term, you know, this the L dot S term is there, and this other part is the function of R, right. So, I have written this function of R L dot S. Okay. So, if you take here dV by dr is there, so your V is minus Z square by R. So, if you take dV by dr and 1 by R is there, here basically function of R, it is 1 by R cube. Okay. So, now L dot S, so as I discussed earlier, so total angular momentum J is defined as a L plus S vectorial sum. So, one can get J square equal to L square plus 2 L dot S plus S square. So, from here L dot S is equal to half J square minus L square minus S square. Okay. Now, this our wave function was psi n L m L m S. Now, that wave function for this calculation we will not use. Okay. So, we will define a wave function, we will take a wave function that basically psi n L j m j, okay, which will be the eigenstate of H0, L square, S square, J square and Jz. So, psi n L j m j in place of psi n L m L m S. Now, m L m S, because that was m L is basically it was m L it was related with the L angular momentum L, and m S it was related to the spin angular momentum S. Okay. Now, since we are replacing this L dot S in terms of J L S, so we have to consider a suitable wave function which will be the simultaneous wave function of this J square, L square, S square and of course H0. So, and other Z component, this is Jz. So, that's the psi n L j m j. It is a simultaneous wave function of this operator, and it's if you operate this operator on this wave function, we get the eigenvalue H0, this gives En, L square give L plus 1 H cross square, S square give S plus 1 H cross square, J square gives J square. If we apply on this wave function, it will give the eigenvalue J plus 1 H cross square, and Jz will give you Mj H cross. Okay. So, this so one has to consider the suitable eigenfunction or identify suitable eigenfunction, okay, or wave function, and then one can use that wave function for calculating using the perturbation theory. One can find out this the correction to the energy due to this H2 Hamiltonian, yes. So this expectation value of this H2 one has to find out. So again this is the H2 term, okay, H2 term, and again psi star, this H2 psi, here psi is, as we have taken this NL psi NL J MJ, and if you proceed then this actually this R FR, function of FR, so it is not the eigen operator, okay, for this wave function. So one has to find out the expectation value. So that's what I have written in this bracket, okay. So one has to find out FR, and here obviously you are getting this eigen value J plus 1, LL plus 1, SS plus 1, okay. Now in function of R, basically whatever this 1 by R cube is there, so one has to find out this expectation value of 1 by R cube for this wave function, and if you calculate, so ultimately for this if function of R, expectation value of function of R will come this, okay. So now if you use this expectation value of R, this function of R, so that if you put here, so ultimately you will get this correction term del E2, and as I mentioned that it is for this term is valid for L is not equal to 0, because L dot S, this spin orbit coupling is there, it will exist only L is not equal to 0. So for L is not equal to 0, whatever the correction energy we got, that is the correction to the potential energy due to spin orbit interaction. So del E2 equal to minus En z square alpha square by 2 n L plus half L plus 1 into L when j equal to L plus half, or into minus L minus 1 for j equal to L minus half, okay. S is plus half or minus half, so that is why j. So so depending on the j value, so either this term will be multiplied by L or minus L minus 1. So depending on the j value, okay. Now this term vanish when L equal to 0. So del E2 equal to 0 when L equal to 0, and del E2 is equal to this when L is not equal to 0, okay. So this is the second correction due to the spin orbit coupling, and then come to the third correction, okay. H3 is this, and that term, this is valid for L equal to 0, because this delta R, delta Dirac function, it is 1 at R equal to 0, equal to 0 at R is not equal to 0, okay. So that I have shown you that only possible that R equal to 0, only this, when L equal to 0, then only this wave function R in 0, it exists at R equal to 0 when L equal to 0, okay. So basically this one has to find out this expectation value for this H3, and so here you have to take the wave function, right. So which wave function you will choose? So only psi n 0 0, okay. When L equal to 0, obviously other ML will be 0, whatever MS will be 0, okay. MS will not considered whether it is there or not, does not matter. So because important is L equal to 0, okay. So only this term exists when L equal to 0, and when L is not equal to 0, So, this term will not exist. So, del E3 will be automatically 0. So, if you evaluate this, so psi n 0 0 means R n 0, okay, that what is the wave function that we have seen for the hydrogen atom we have seen. So, this basically it is the this psi n 0 is basically this, okay, or square of it is this. So, we are getting del E3 equal to minus E n z square alpha square by n for L equal to 0. So, using the perturbation theory and then the normal how to find out the expectation value in quantum mechanics, using this procedure one can get this energy term for the Dirac equation. So, ultimately our Dirac equation is Dirac-Hamilton is H equal to H0 plus H1 plus H2 plus H3. Okay. This is the approximation up to term V square by C square we have considered, and psi n j m j is the ultimate wave function for this Hamiltonian, Dirac-Hamiltonian, and if you apply this Dirac-Hamilton on this wave function, you will get the energy E n j psi n j m j. So, this is the eigenvalue equation, you know, and this energy E n j, it basically it equal to energy comes from H0. So, this is E n, and this comes from other correction term delta E1 plus delta E2 plus delta E3. Okay. If you add them, so you will get basically E n j equal to E n 1 plus z square alpha square by n square into n by j plus half minus 3 by 4. So, this expression already I have shown you earlier, okay, using the vector model. So, we have considered LS coupling and we have modified the energy, okay, just I mentioned. So, but how it comes? So, just we mentioned that in case of Bohr-Sommerfeld model, whatever the energy terms we got, so this J, in place of J it was basically L. Okay. Now, just we mentioned if L can be replaced by J, okay, when we will consider the vector model for LS coupling, and we get the total angular momentum, this is J equal to L plus S. Okay. So, that is why just from similarity I wrote this energy expression, but now this energy expression has come automatically from Dirac equation, and that is the ultimate energy expression which tells about the energy levels in hydrogen like atom, and transition among these energy levels, that gives the spectral lines, and that spectral lines is basically whatever it is, spectral lines due to fine structure, or that can be explained using this energy expression E n j, which has come automatically from the Dirac equation. Okay. So, what ultimately we got this from Dirac equation, we got the energy expression, and also we got the wave function, eigenwave function psi n j m j. So, but we are interested to deal with this energy expression. In this energy expression, individual terms here I have mentioned, already I have discussed. So, delta E1 relativistic correction to kinetic energy, delta E2 that spin orbit interaction correction to potential energy, and this is the Darwin correction. Okay. And this for potential energy, this correction. So, this for L is not equal to 0, this is del E2, and L equal to 0 del E3. So, del E2 and del E3 gives the complete correction term to potential energy. So, one active for L equal to 0, other is vanish, and other is active when L is not equal to 0, and next one Darwin term will vanish for L is not equal to 0. Okay. So, this is the solution for Dirac equation, and just I for the sake of completeness to the discussion, so I showed you the mainly result following the logic without calculating in details. So, details calculation I avoid, just because for that you need really knowledge of quantum mechanics, advanced knowledge of quantum mechanics. Okay. So, but I left for you for future. So, ultimately what we got? Ultimately we got this we can energy expression means we can get energy spectra, okay, of hydrogen like atom. So, or we have seen so far that for non-relativistic spinless case, energy is En equal to minus m mu, just I have written m z square e to the power 4 divided by 2n square h cross square. Okay. So, the same result basically is from Bohr model and also Schrodinger equation. Okay. And then next case is relativistic spinless case. Okay. So, ENL basically, that is En plus del E1. Okay. If you I know what is En and I know what is the term for del E1. Okay. Del E1 is this and En is the En. So, En plus this del E1. So, En, if you take common, 1 plus this rest of the part. So, that is what I have written here. So, 1 plus z square alpha square by n square, n by L plus half minus 3 by 4. So, this same result as we got from Bohr-Sommerfeld model and Klein-Gordon equation. Okay. So, Klein-Gordon equation, if one solve relativistic equation, so one can get the same result. So, that I have not shown. So, so this is the relativistic but spinless case, and relativistic and spin case. Okay. So, that is the solution of Dirac equation, and that energy expression Enj equal to 1. So, this En plus del E1 plus del E2 plus del E3. Okay, if we add all of them, so each correction term we have derived. So, now if you add all of them, you should check it. Okay, then you will get Enj equal to En 1 plus z square alpha square by n square, n by j plus half minus 3 by 4. Okay. So, this the this similar result I told when we consider the vector model. Basically, to find out the total angular momentum using the vector model, J equal to V plus S. Okay. And this same result we got from the Dirac equation. Okay. Now, in case of relativistic, in case of non-relativistic spinless case, so for just if we consider n equal to 2, so this is the energy level. Okay. And for n equal to, what are the spectroscopic term? So, n equal to L equal to 0 1, and then J will be half and 3 by 2, L plus half, L minus half. So, it is half and 3 by 2. So, this spectroscopic term you will get this n equal to L equal to 0 S. Okay. So, J will be half. So, 2s half, this is one spectroscopic term state, and another L equal to 1. So, P 2p. Okay. So, J will be half and 3 by 2. So, J equal to, so 2p half, 2p 3. So, L equal to 2 basically as per the energy of these 3 states, 2s half, 2p half, 2p 3 by 2, these 3 states will have the same energy, Okay. Now, if you consider the relativistic correction, if you include the relativistic correction, now degeneracy will remove. So, they are degenerate, same energy they are. So, degeneracy removed, but here in this correction term, it's, you can see it does not depend on J, it depends on only L. Okay. So, that is why S and P, it will consider S and P, it will not differentiate P half and P 3 by 2. So, P half and P 3 by 2 will have the same energy, okay, whereas this S half will have the different energy. Now, S half, it is, you see, this from the original energy it has come down, both has come down, because this term, this red line, dotted line is basically this term En. Okay. Now, additional term L, when L is smaller, so this term will be higher. Okay. So, it is so En is negative, so it will add more negative to the En, so it will come down more. So, that is why half, this 2s half is here, whereas this 2p half or 2p 3 by 2. So, L is higher, so this term will be smaller, so less negative. So, this term it will add less negative. So, but it will add some. So, it will come down, but it will be this value, it will be smaller than the this other value, okay, for S 2s half. Okay. So, that is why this now this energy level, it was degenerate for these 3 states. Now, the degeneracy is removed in some extent, but we are getting 2 energy level, one is for S half, another is for P half and P 3 by 2. Okay. Now, if we consider just from this original En, okay, now if you consider this other correction, say just only del E2 correction, okay, D2 del E2 correction, this spin orbit interaction correction. So, then in this expression you can see it depends on L, okay, it depends on L, but this correction del E2 is 0 for L equal to 0. So, S, so this whatever the original energy for 2s half, so this it will remain the same energy 2s half, but other P 3 by 2 and P half, okay. So, one has gone up and one has come down, because here this term, negative term, this is the negative term. Now, it is multiplied with L for J plus up. Okay. So, when you multiply it by L, okay, so this is for L plus up, means P 3 by 2, you can consider for in case of P 3 by 2. So, this is negative. Okay. This is negative. So, this term, this is negative. Okay. So, already whatever the negative energy was there. So, now so this term already negative, this term, this En, it is there, it's a negative. Now, negative into this negative, there to be positive. So, some addition with negative energy, some additional positive term is added. So, it will go up, okay. So, that is what happening. And other case, when J equal to L minus half, means J equal to half P half. In case of P half, it is minus L minus 1. that means it will be plus, En this will be plus term. Okay. So, in general this whatever the negative energy dotted lines are there, so some more negative part is added with it, more negative part slightly added with this, so it will come down. Okay. So, for P3 by 2 some small positive term was added with negative, so it has come up, is reduced the negative value. Okay. And it P half it increased the negative value. Okay. So, now you see that due to this correction, spin orbit interaction correction, so P3 by 2 and P half they are separated. Okay. So, this is due to the relativistic not relativistic spin orbit interaction correction. And other Darwin term. Okay. In case of Darwin term, you can see it's this term is 0 for L is not equal to 0. So, obviously P half and P3 by 2 will not be affected. So, it has original energy. See, it coincides with the red dotted line, original energy for P half and P3 by 2. But S, this term has gone up. Why? This term again it is negative. Okay. This del E3 is negative. Okay. Now, when it is negative, as I told already, En, this red term negative term. So, now here this earlier it was plus term. Okay. When it is plus, so more negative term is included there. Now, because of this minus sign, so whatever the original negative minus sign, now some positive correction term is added with the negative value. So, that is why it will be less negative. So, it has gone up. So, now 2s half is basically separated from this P half and P3 by 2. Okay. So, these are the effect of different correction term on the spectral energy level that I have shown individually, but individually we will not see, we will see ultimately the total effect, and this for total effect, that is the energy level. So, here basically this ENJ, it does not depend on L, so it depends on J. Okay. So, for same L value, that is yeah. So, only we have to see this J value of this term and N value. So, N is same for all N equal to 2. So, now J value, we have 2 J value, one is half and another is 3 by 2. So, this P3 by 2 is separated from the P half and S half. Okay. So, here obviously the same, when J is smaller, so this term will be higher, so it will be more negative. So, this is the lower energy than this P3 by 2. So, this is the ultimate splitting of this. Now, here you can see this S half and P half, these are having the same energy, but Rutherford and Lamb, they did experiment microwave experiment, yes, I think they use this I think radio wave, it's the longer wavelength, lower frequency. Okay. Radio wave experiment, and they found that this S half and P half is not basically having the same energy. P half is shifted upwards from the S half shifted upwards from the P half. So, they are not having the same energy, they have some energy difference. Okay. And this energy difference, this shift, the shift of S half from P half, as per the Dirac theory, it should have the same energy, but in reality radio wave experiment shows that they do not have the same energy. This S half is basically shifted upwards from the p half. That means they have different energy level, but this difference is very, very small, and this shift as per Dirac equation they coincide, but Lamb and Rutherford discovered experimentally that there is a shifting of S half from the P half. So, this shift, this is called Lamb shift, and as earlier just I mentioned here, automatically it has come out that so originally in as per the Dirac theory, so P 3 by 2 and P half S half, so they have the two energy level. So, this is P 3 by 2 and this is another is for S half and P half. Okay. But for radioactive correction to the Dirac theory, if that is theoretically also calculated and experimentally it is found. Okay. So, if one consider the radioactive correction to the Dirac theory, then it shows that this 2s half and 2p half they have different energy, and 2s half is shifted upwards from the 2p half, and that shift is basically Lamb shift, that shift is basically Lamb shift, and this separation is very small. It is the 1057 megahertz. Okay. It's very small frequency, and explanation of this is slightly difficult for you, but this is the experimental fact. But just let me tell you explanation. So, this type of shift, as I told, that this comes from radioactive correction, radioactive interaction. Okay. Now, explanation is that this type of shift is coming due to the interaction of electron with 0 point vibration of electromagnetic field in vacuum. What does it mean? If you remember this simple harmonic motion, harmonic oscillator. So, harmonic oscillator we tell this earlier it was n h cross kind of things. Now, from this quantum mechanics it's come energy expression En equal to n plus half h cross. Okay. Even n equal to 0, then energy is half h cross. So, this is called 0 point energy. Okay. So, similarly in electromagnetic field also, in vacuum there should not be any electromagnetic field, right. There should not be any electromagnetic field. It is just similar to this 0 point energy of harmonic oscillator. For n equal to 0, there should not be any oscillation, any energy, but it is there. That is why it is called 0 point energy. So, it has come from quantum mechanics. Okay. Classically, you cannot think of it. Okay. If there is no this, if n equal to 0, so from where this vibration will come, oscillation will come. But quantum mechanics tells that no, there will be like T equal to 0 at 0 temperature. So, there should not be any energy, vibration, any movement of this oscillator or atoms in the solid, but quantum mechanics it is there. So, that is why it is called 0 point energy. So, similarly in vacuum, we are telling vacuum, so from where this electromagnetic wave will come. Okay. So, but it is possible in quantum mechanics, and so that is why it is called the 0 point vibration of electromagnetic field in vacuum. And from quantum electrodynamics, classical quantum electrodynamics, it is shown that this energy, this correction due to this radioactive radiation or electromagnetic field, so this correction in vacuum, so its expression comes like this. Okay. So, here in this expression one can see psi 0, psi 0 term, okay, means L equal to 0 this term. So, so this term only exists for L equal to 0. For other value of L, it does not exist, and this basically tells about their connection to this. As I mentioned this, in case of only r equal to 0, there is the existence of psi, okay, and this psi is basically that existence of this psi only for L equal to 0. So, that's here just I have shown. So, this lamp sheet is connected with that one. So, so it's called Darwin term. So, this again it's related with the Darwin term, and this comes so when see the importance of the wave function, you know, this not only energy expression, but wave function also important. That's what I was telling, that solving the Schrodinger equation, we got the same energy expression. What else we got? I told that we got the wave function. This wave function also gives very important information, and that's why there when we study the wave function, that we have seen the variation of the wave function as a function of r, and we have seen that only wave function exists at r equal to 0 when L equal to 0, okay, and now when L equal to 0, so Darwin term exists, and then this vacuum correction term exists here, whatever I am showing, okay. So, and this is basically this is connected with the interaction of nucleus and the electron. So, basically what happened, this this we can tell like this, there is the as a result of the interaction with vacuum, electrons begins to vibrate in its orbit, which cause it to spread out in space, okay. So, there should not be any vibration in vacuum in terms of interaction with the electromagnetic field, but since 0 point vibration of electromagnetic field exists in vacuum, so electron basically vibrates, even if in vacuum electron begins to vibrate, electron vibrate, and when electron vibrate, so when electron is stationary in a orbit, so fine. So, this interaction between the nucleus and electron will be whatever. So, that will be affected when this electron is not point electron on a orbit, it is a spread over, say spherically spread over on a region, and that will basically affect the interaction, and in principle, in fact, this vibration cause it to spread out in space. So, its interaction with the nucleus becomes weaker, and the stationary energy levels are raised. So, energy level, okay, energy, it depends on the potential energy, right, Vr, okay. So, now how, so potential energy tells about the interaction, okay, between the two charge, okay, interaction between the two charge, okay. Now, here electron and the nucleus. So, potential energy, it tells it's whether it is weaker or stronger. So, it depends on the interaction between these two charge. One is electron and one is nucleus. So, when this in place of point charge, when it oscillate, vibrate, so it becomes is spread out, and then the interaction with the nucleus is become weaker. When it becomes weaker, so its energy value of the energy level, it's basically it's increased, means it becomes less negative. so it become positive, it goes up. Okay, so that's why, and it happens only for s orbit, s energy level, because in case of s L equal to 0, we have seen the existence of the existence of the energy of the wave function. Okay, existence of the wave function at r equal to 0. So this only this that it tells that for this s energy level, it is affected due to the interaction with the nucleus. Okay, and this interaction with the nucleus, it is changed because of the changing of the nature of the electron density. Okay, if it is stationary, then fine. If it is not stationary, then it is spread out as it is predicted that due to the 0 point oscillation, it will spread out, and then this interaction will be weaker, and then S level will go up. So that's why that is the nothing but the lamp shift. Okay, so this way it's not very clear explanation I will be able to give you, but just because one has to know quantum electrodynamics, etc. Okay, to understand more in details, but this the phenomenologically I can tell you the explanation of lamp shift. Okay, so I will stop here. Thank you for your attention.